Share Time Series project by Kay Ayala and Pankaj Kumar. For this project, we used data from a bike share service in Washington, D.C. We pretended we were employees of the City of D.C. Transportation Department. We wanted to know the impact our road construction project in the next half year would have on cyclists in the city. To do this, we wanted to find the best model to forecast the total number of bike share users for the next half year. Our data had a number of variables we could utilize. However, we focused on predicting the total number of users from a metric of wind speed and a metric of temperature. The realization for these variables can be seen in the center graphic. Above that, we have the realization, ACF, and spectral density for total users. We can see something that looks like seasonality in the total users realization. It also looks like there might be wandering, but because this is daily data over 2 years of observation and it follows the temperature data, it's clearly influenced by the weather seasonality. Due to this, even though we have only one realization for total users, we can say this realization is likely non-stationary because the mean depends on time. As for variance, it appears the variance may change over time. The variance is a little bit smaller at the beginning and a little bit larger towards the end. This again is evidence for stationarity, but we only have one realization, so we can't get a really good estimate of this. Now let's take a look over at the ACFs. These are slowly damping, and there's also some difference between the ACF from the first half of the data and the ACF from the second half. These are indications of non-stationary data. We did our first analysis with an ARMA model. Even though our data does not appear to be stationary, we hope that this would provide a benchmark for the ASE, which we could beat with successive models. The AIC and BIC both picked in ARMA 2.1. The ACF of the residuals is fairly white, and the realization of the residuals looks at least in the ballpark of white noise. We don't have it on the slide, however, the Elljung box test did not reject the null hypothesis of white noise. Here's our ARMA 2.1 forecast. We can see that the slow decay to the mean, as we would expect from an ARMA model. Our ASE was 4,526. This is the benchmark we will be using to compare to our other models. We tried modeling an ARIMA model next. I would like to take a moment here to say that we tried an ARIMA model with yearly seasonality as well, but the results were so similar to the ARIMA we chose to just represent the ARIMA model. For the curious, our ARIMA model can be found in the R Markdown file. Okay, on the left we can see the results of the first difference. The results here are fairly close to white noise, but we wanted to try to capture that remaining signal with the AR and MA components. The BIC chose a P equals 1 and Q equals 1. After removing these elements, we can see that the ACF looks fairly white. The ARIMA forecast appears nearly identical to the ARMA forecast. It has an ASE of 5,378. Strangely, this model has an even higher ASE than the ARMA. Next thing we tried was a VAR model. Now this, we just assumed we would have access to the predictions of wind speed and temperature for our forecast. With this assumption, we are able to calculate an ASE for the VAR model, and it came out to be 5,542. Now this is even higher than the one for the ARIMA. So we tried a neural network. We just left it with the default parameters, and this seemed like a reasonable choice since the ARIMA and the ARIMA models didn't give us very valuable predictions. Those are the two models we would have looked at to inform us about what the hyperparameters were to set for this model. The forecast on the left initially looked like it was replicating the shape of the realization really well, but after looking at the forecast to the right, it was clear the prediction was too low. In the plot on the left, it looks like there are two distinct sets of predictions. One goes low and the other is much higher. I wonder if there's a way we could tune the hyperparameters in order to get the higher set of predictions more consistently and consequently raise those predicted values. Even though the forecast looked like it was capturing the shape of the realization, the ASE was 12,526. This was the highest of all the models. For the ensemble model, we took an average of the VAR and ARMA models. This had an ASE of 4,814, which was our second lowest ASE. Of all our models, the ARMA 2.1 model had the best performance in terms of ASE. This is counterintuitive because the data appears to be fairly clearly non-stationary, and the ARMA models are stationary. Our second best model was the ensemble of the ARMA and VAR models. Our third was the ARIMA, and then the VAR, and in last place, the neural network. For the purpose of determining the number of impacted cyclists for the construction project, we can suggest the ARMA 2.1 model. For longer forecasts and for lay people, we would just recommend using the mean, which is what the ARMA model will eventually predict anyway.